Welcome to Summarize Science, where we break down the latest fascinating research. What happens when two supermassive black holes, millions of times heavier than our Sun, are set on a collision course? They begin a cosmic dance, spiraling closer and closer over millions of years. But there's a well-known problem. They often get stuck. This is known as the final-parsec problem, a major puzzle in astrophysics where these titans stall about a light-year apart. At this distance, they can't lose energy fast enough to complete their final merge within the age of the universe. But what if there's a hidden force at play? A new research paper explores the fascinating idea that these black holes might carry a type of dark charge. This isn't like the electric charge we know, but a new property linked to the mysterious dark sector of our universe. If black holes have this charge, the theory goes, they should emit a completely new form of energy as they orbit each other. The researchers call this dark dipole radiation. Think of it like an extra exhaust pipe on a car. It provides another way for the binary system to shed energy and momentum. By losing energy faster through this dark radiation, the black holes can overcome the stall and accelerate their spiral. The effect is especially powerful for black holes in highly eccentric or oval-shaped orbits as shown in these figures. So, how could we possibly test such a wild idea? The answer lies in listening to the universe's gravitational hum. All the supermassive black hole binaries across the cosmos create a constant, low-frequency background of gravitational waves. We can detect this faint signal using something called a Pulsar Timing Array, which uses hyper-precise cosmic clocks to spot these tiny ripples in space-time. This new dark radiation would change the sound of that cosmic hum, altering its spectrum in a specific, predictable way. The researchers built a model to predict what this modified gravitational wave background would look like. Then came the moment of truth. They compared their model to the latest, real-world data from pulsar timing arrays like an nanograph. As you can see here, their models are plotted right against the observational data points. They found that while this dark radiation alone might not be enough to completely solve the final parsec problem for all black holes, it definitely helps. Most excitingly, the actual observational data seemed to prefer a model that included this dark dipole radiation over the standard model without it. So let's recap the important points from this study. First, supermassive black holes might get stuck before they can merge, a problem that has puzzled astronomers for years. Second, this paper suggests a solution involving a hidden dark charge that causes the black holes to emit extra energy, speeding up their merger. Third, this process leaves a distinct fingerprint on the gravitational wave background that we are now able to observe. And amazingly, the first bits of data hint that this might actually be happening, as the model with a dark charge provides a better fit. This could mean that black holes are not just objects of immense gravity, but also windows into new physics beyond our current understanding. For now, the evidence is just a tantalizing hint, but future observations that can listen to even lower frequencies will tell us if black holes truly carry a secret dark charge. Thanks for tuning in to Summarize Science.